is functional first, because we run functional simulation first. But we got one thing that most people don't have, which is the feedback. And we're going to show a couple of examples, a couple of results of why it's very interesting to have feedback. So what is feedback? Feedback means that after certain amounts of time, you ask your CPU timers, and they tell you, oh, well, I'm not doing anything. I'm idle. Okay, so you go back to the idle days IPC, or someone says, no, I'm going to add 2 IPC, I'm going to add 4 IPC. So you give that information back to SimNow, and SimNow uses that information to schedule more instructions in the next quantum with respect to the other processor. So if one processor is going for IPC, means that that application is going to go faster. If you have 2 CPUs and you run 2 totally independent applications on each one of them, and one had an IPC of 1 and the other one had an IPC of 2, this one is going to consume twice of the amount of instructions, and it's going to eventually finish in 4. And another of the good things of having time and feedback is that most of the simulations from the rest of the experiments, we're going to be running an application until completion. It's a very small application because we have to fit it into the 5-minute time that we have here. But that means that the way of measuring how much time it took for that application to finish, it's using the user being time. So we use user being time inside SimNow, and it's going to tell us how much time it took. So if you change your memory hierarchy and you put a memory hierarchy that's much slower, it's going to take more time. And that is interesting because that's what we call timing feedback, because if the simulator didn't give timing feedback, it's okay for simple-scalar because just one application, just one thread, doesn't really matter. There's not many points in time in which you're waiting for this for an overall network. But if you have a system, the operating system is going to schedule your threads, it's going to schedule your application based on many different reasons. So if you're waiting for this, you're waiting for this. And if you're very fast, and here's an application that if one of your threads is going faster than the other one, eventually you're going to have to wait. And that is important in a multi-threaded environment to know that this thread took longer to take here and this one is waiting. And that's why we think that this kind of approaches is much better than having the monolithic approach in which there's totally open loop and it's like you don't get this into account. Okay, so what is this simulation that we got here? This is full timing. Okay. So we run an application. We run this application, which is stored in a bash file. I'm going to open this bash file immediately. And basically what it tells him now to do is get the file that is in the local host at R, copy it inside your system, and then execute it. Okay? So I'm going to open. Who produces that file? Okay, here's where we produce it. By the way, all this is totally handled by COTSon. So most of these details is that so that you get to understand the philosophy that's behind all this. But you don't have to get into this complication every time you run something. Basically what we're doing here is we're writing a file which is saying execute the 349 read runtime to, which is something I hacked up that is mread running an mread input, which is even smaller than the test input that you get for mread, so that it finishes in 2 seconds in the host, and it is enough for us. Then at the end you get the output, which is stored in out. If you were able to see that inside what runtime it does, that runtime is putting all this output in out, and we copy that output file and we put it into the temp out of the host. And then we also copy a file into temp finish. And here we're using another kind of finishing an application, which is by looking for a particular file in the host system. The exit trigger is something that eventually, the same thing as the max samples or the max nanos, which is, I don't know if we've definitely seen examples of max samples, which is execute so many samples and then stop. We also have the max nanos, which is executes for so many nanoseconds and then stop. And then we also have the exit trigger, which says something like, okay, execute until you find this file. And that's a way of, I don't care how many seconds or how many samples this application takes, but eventually this application is going to write this thing here. That's where my spec is going to finish. I want all those numbers there. So this is how it's going to finish. And I think this here Yeah, this uses one timer that we use constantly, which is timer 1, which is without distribution. But it's not very interesting. I'm not very interested now. I cannot execute this now because this takes approximately 1 hour and a half to finish. And this is what it would take 2 seconds of full simulation on single scalar or something like that. You execute, I don't know how many instructions or whatever, but it takes a long time. Depending on this notebook is very slow, so if you have a faster machine, it may take less, but still, this application is not representative of anything. It's just an example that we put here, but I can tell you, the first part that's just underneath, the first spikes that you see here, you see the the IDCs of the both CPUs counting idle time. It's not really what the timer says, but it's the instruction count that SIM now tells us, which of course is directed by what our timers are telling us. So first we got some spikes, which is basically the X get it and the X boot. Then we got a smaller period amount of time. That small period amount of time is underneath is milliseconds. Basically there we are loading the shell script that's going to execute everything. Then inside the shell script, that other part, exactly there, that's loading the application, which is something that happens and takes time. And then that part over there is one of the threads starting execution, and basically this is SEMGRID, which is highly parallel, and sends data to the other thread, and 2 cores, so both cores start to be, I think yellow is CPU2, although CPU2, as you saw before, CPU1 in the figures is the one that really is in taking care of the shell. And then you got like 5 spikes, 1, 2, 3, 4, 6 iterations of this mgrid, and it finishes. Okay, so let's go to the next one. This is exactly the same simulation without feedback. Without feedback means that we run the simulation, we give all the information to the timers process everything, but we don't use that information to say anything back to SIMNow. So both of these simulations are going to produce log files, are going to produce the metrics out. If you let me. One of the things that can be seen here is that instead of using the file last, we are saying I want the file. So that means that after each sample, you're going to get one file with all the data. We have versions of this that put it all in the database and that you can find. Most of our monitors and tools hook up to the database. But here, I was using this so that you can see, if you see the output, full timing, okay, log. So here we have all the log files for the 1728. It's not for the, okay, 1728. So those are all the samples. The other one is going to have another different kind of samples, but it's going to produce them all out. The main problem with not giving feedback to SIMNow is that SIMNow doesn't know how much time it takes to wait, or how much time it takes to do anything if we don't tell it to. So all the time it takes to really load the application, mainly it's waiting. So if you're going to go at that application, at that specific point in time, at one IPC, our metrics show that our timer is saying that you should be going at